Well, hey physics folks, welcome to Doc Oncoat's Physics. Today what we're going to be taking a look at is the diffraction of light through something called a diffraction grating. A diffraction grating is really nothing more than something with some openings in it. And what we're going to be looking at today is the diffraction of light through a diffraction grating with two openings. And what you can see over here on the left, and I'm going to choose, see, maybe a yellow color here, is we have an opening here and we have an opening here. And this is our diffraction grating. Okay. This is the grating, this black line here. And the openings are the slits in the grating itself. And as we talked about in the lesson on diffraction, there is a formula that we use, and that formula is right over here on the left-hand side. And it's a reasonably simple formula. And the formula has got four variables. It's got d, which is the distance between the openings, right? So this is d. It's got theta, which I'll go into in a minute. M, and then if we take a look at the right-hand side, there is the variable m. M is the number of the dot, right? It is the fringe number, if you will, of the dot of something that we would see on a screen some distance away. Okay, so m can be 1, 2, 3, depending on what dot we're talking about. We're going to restrict it to m equal 1 or m equals 2. And these dots can be on either side of this thing called a central maximum. Okay, so that's the m. M is simply the fringe number or the dot that you see on either side of the central maximum. All right, so that's the variable d. All right, that's the letter m. Lambda is simply the wavelength of the light, right? It's the wavelength in nanometers of the light that's going to be incident on the diffraction grating. Incident means it's just going to hit the diffraction grating, right? And we're assuming that the wavelength of the light is monochromatic, so it's all simply one wavelength. It's not like a flashlight that we turn on and we have you know, light of a whole variety of different wavelengths that comes from the flashlight. We're assuming it's something like a laser, and so it's got simply one wavelength of light. And so that's what the lambda is. Now, what is theta? Well, theta for our purposes is, let's see if I can draw this well here. If I were to draw a triangle here, right, so I have a line from here out to m equals 1, and I have a length L here, which is the distance from my diffraction grating to the screen, then theta is this angle right in here. Okay, and we don't need a Java update, so we'll get rid of that. Theta is simply the angle that is in this triangle here. So those are all the variables that make up the equation. Okay, so let's say, and we'll scroll down, we'll get a nice clean problem screen here. Let's say that we have a monochromatic light source, which we're always going to have, right? And it hits a diffraction grating that's got openings. The openings D are equal to 0.006 millimeters, right? So 0.006 millimeters. Okay, so that's the opening between the slits in the diffraction grating. And the first order fringe over here, so m equals 1, right, is going to be 9 centimeters from the central maximum. So this height here, all right, we're saying it's going to be 9 centimeters. And we have a screen that's 3 meters away from our diffraction grating. So this distance here is 3 meters. Okay, so we're getting all the geometry down now. And we would like to know what the wavelength lambda is going to be, or has to be, of the light in order for this all to be true. Okay, so one of the first things I'm going to do is I'm going to draw a line, and we'll draw a better line this time. And our line is going to start there and end up there. Okay, so here's our triangle. All right, I'm going to go to different size here. There's our triangle, there's theta. Okay, so what do we know? Well, we know D is equal to 0.006 millimeters. But do we deal in millimeters in physics? No, not really. We're going to have to convert that to meters, all right? And so we're going to convert this to meters, so this becomes 0.000006 meters, because we have to divide this number by 1,000. So we have D. We have M, all right? We've already said that M is equal to 1, all right? So this is M over here, all right? So we've got that. We're looking for lambda, all right? So what else do we need? We need theta, all right? Can we get theta? Can we get this angle theta right in here? Well, we have a triangle here. We know that the opposite side over here is 9 centimeters. We know the adjacent side to the angle is 3 meters. So using the inverse tan function, we can find out what the angle is going to be. So the inverse tangent of 0.09 meters divided by 3 meters, and remember that this is 9 centimeters over here, but we need to convert this to meters. And so when we do the conversion, the inverse tangent of 0.09 divided by 3 meters comes to be 1.71 degrees. So now we know theta is 1.71 degrees. Okay, so we have D, we have M, we have theta. We should be able to get lambda, right, just by plugging in the variables. So let's do that. So on the left-hand side we have D, which is 0.000006 meters. Okay, we have lambda. So I'm sorry, we have theta times the sine of 1.71 degrees is equal to M, which is 1, times lambda. So when we calculate the sine of 1.71 degrees and we multiply that by 0.000006, we get lambda to equal 179 nanometers, or 179 times 10 to the minus 9th meters. Now on your calculators, you may come up with 1.79 times 10 to the minus 7th. Right? That's the same as 179 times 10 to the minus 9th. With light waves, we always talk in terms of nanometers because that's the way scientists talk about light waves. We always talk in nanometers. So this is problem 1. So let's try a different one where we're solving for something a little bit different. We'll scroll down here and okay, so in this next problem, what we're going to do is we're going to take a look at a similar problem, but we'll be looking for a different variable. So in this problem, we're told that a light wave of frequency 6.5 times 10 to the 14th hertz. So we know F is 6.5 times 10 to the 14th, it's a 4 up there, hertz. Okay. Is incident on a diffraction grating with openings that are a distance of 0.008 millimeters apart. So D down here is 0.008 millimeters apart, or if we divide that by 1,000, it's 0.000008 meters apart. Okay, so we have D. So the incident on a diffraction grating that's 0.008 millimeters apart. If the first order fringe, so M equals 1, has a dot showing on a screen that is 1 meter from the grating, so L here equals 1 meter. So that's our length from the diffraction grating out to the screen. How far from the central maximum is the dot? So we want to know this distance right here. We'll call this H, okay? All right, because it's the first order dot, first order fringe. So we want to know what H is. Well, if we want to know what H is, what we're going to need to figure out is what theta is. Let's see if I can draw a semi-straight line here. Because remember, this angle in here is theta. So if I know my length, which I do, and I know my height, which I don't yet, I can, if I know my length, which is 1, I know that, and I know my angle, I can get the height, okay, using trig. All right, so that's not too bad. So let's see what we got. So if we look at our formula, d times the sine of theta equals m times lambda. Well, we know d because that's been given to us. All right, so we have that. We have m, that's 1. All right. We've been given the frequency. All right. If we know the frequency of the light, we should be able to get the wavelength of the light. All right, because the wavelength of the light is simply the speed of light divided by the frequency of that light. So this would be 3 times 10 to the 8th meters per second divided by the frequency, which is 6.5 times 10 to the 14th hertz. Okay, and when we do that arithmetic, what we get is we get a wavelength equal to 462 nanometers, or 462 times 10 to the minus 9th meters. Okay, so now we have d, m, and lambda. We have 3 of the 4 variables. We can figure out what theta is. So let's plug those values in. So we get 0.000008 times the sine of theta, which is what we're looking for because we need theta here in order to get h, okay, is equal to m, which is 1, times lambda, which is 462 times 10 to the minus 9th, okay? So let's divide each side by 0.000008, and we could figure out what theta is. And theta now turns out to be 3.3 degrees when we solve the equation for theta. So we're almost there. Now what we want to know is we want to know what h is. Well, we know what L is, right? We know the length from the diffraction grating to the screen. That's 1 meter, right? We now know theta is 3.3 degrees, right? Which trig function should we use? Well, we have the adjacent side. We're looking for the opposite side. That means tangent. So the tangent of 3.3 degrees is going to be equal to the opposite side, which is h, divided by L, which is 1. Okay, so if I can figure out the tangent of 3.3, multiply that by 1, I can get h. And the tangent of 3.3 degrees turns out to be 0.057 or 0.057 meters or 5.7 centimeters. So the distance here from the central maximum up to the first dot or the first order fringe is 5.7 centimeters. Okay. So that's how we solve these problems that have to do with diffraction gratings with multiple openings, 2 slits. Usually most problems have 2 slits, and we're looking for bright order fringes. Okay. Again, the equation right here, d times the sine of theta equals m times lambda. Sometimes we've got to use a little bit of geometry in here, which is not a big problem, right? Since we know trigonometry, we can use the tangent function, we can use the sine functions, and we can solve the problems that way. I hope that helps, and we'll see you next time.